area of 12 square meters, right? Total surface area. So I now need to come up with the constraint equation. The thing that's going to confine where I'm allowed to look here, right? Because if I say build me a box XYZ, you're free to let XYZ be whatever you want. But here we have restrictions, right? This total surface area can only be 12 square meters. So my constraint is that when you look at the surface area of this thing, which is going to be this front side and back side are the same, right? This is x times z. The back one is x times z. I have two of those. So 2xz's plus, then I have a side, two sides right here, that, and then this one right here. Those are both y times z, right? Y times z. That's the area of that, and I have two of those. Plus, I have the bottom of the box, right? Only the bottom, not the top. So the bottom of this thing down here, that thing in there, that has the dimensions, the area of x times y, and I only have one, so xy. I know that that added up together has to be 12. Do you see the constraint? Do you see this is exactly what we've been doing now? We have what we're trying to optimize, find the maximum of, with this constraint equation. And so we're just going to run through the same thing we've been doing. We're going to do Lagrange. The g of x, this is the g of x, y, z right here. That's our g. And this one was really acting like the f that we had from before. Okay? All right, let's set up some equations. Hopefully this one won't be as bad as the last one. May I erase? Yeah, we're good. Let me put it up here. V of x, y, z equals x, y, z. All right. First equation that I'm going to have, I need the partial of v with respect to x equals lambda times partial of g with respect to x. Second equation, partial of v with respect to y must equal lambda partial g with respect to y. Third equation, partial of v with respect to z must equal lambda times partial g with respect to z. And then my fourth equation is that equation. And now I go to town with my partials. Partial of v with respect to x is going to be yz equals lambda. Now be careful, partial of g with respect to x, be careful here. 2z plus y, because there's no x's in here. So 2z plus y, that's two terms. So I need to put it in parentheses, 2z plus y. Let me double check. 2z plus y. Got it? Okay, now I need the same thing here for this one. Partial of v with respect to y is going to be xz equals lambda. Now partial of g with respect to y, I'm going to get 2z plus x. And it's two terms again, so I'm going to put it in parentheses like that. And then my third and final one will be xy equals lambda, and then partial of g with respect to z will be 2x plus 2y in parentheses. Looks a little different than what we've had before, right? Now right off the bat here, I have some really nice conditions I can put onto the problem without having to look at this as like a scenario. Do we all agree that this problem makes no sense if x, y, or z, if any one of them is negative? And none of them can be zero, because if any one of these is zero, we don't have a box anymore, right? So I can say, like, not as a suppose, but as an actual condition of the problem itself, is that x, y, and z all must be greater than 0, or else this problem doesn't make any sense, right? So that's not a suppose, that is a condition of the problem. Now that's really nice, because if I can suppose that, then, well, I don't know, there are different things I can do. Did y'all like what I did a moment ago where I made all these look the same? Do y'all want to do that? We can do that. Like this is yz, that's xz, that's xy, so I can make them all look like xyz, and then set them equal to each other again. And I don't have to suppose that x isn't 0, y isn't 0, z, because I already know that. Okay, so I'm going to do that. Is that all right? So this first one becomes, multiplying both sides by x, we get xyz. Oh, xyz equals, I multiplied both sides by x. I'm not going to distribute it through on the right yet. Just multiply that by x, that by x. I just put it next to the lambda. The second equation, I'm going to multiply both sides by y. So xyz equals lambda y times 2z plus x. And then finally, the third equation becomes multiplying both sides by z, xyz equals lambda z times 2x plus 2y. All right. Now I can start setting these equal to one another and see what happens, right? So let's do these first two. I'm going to do the first two together right here. Let's do those two set equal to one another. That'll look like this. Lambda, let me distribute the lambda x through here. So we get 2 lambda xz plus lambda xy must equal, right? All I did there was distribute it through. Let me double check. Yeah, okay, and then I'm distribute through here. So that equals 2 lambda yz plus lambda xy. These are the same, right? These are the same. So I can subtract it on both sides and it's gone. So these go away. I can now look at what remains here. 2 lambda xz equals 2 lambda yz. Can I divide both sides by 2? Yeah. Yes? Can I divide both sides by z? It's not 0. I can divide by z, right? Only because I have control over the z this time, right? In the very beginning I said z is not 0, so this division by z is actually okay. Now if we didn't have that control, then we wouldn't want to do that, right? But we actually know that we can get rid of the z and the 2 on both of these. Now can I divide by lambda? No, because I don't know anything about lambda. I just know lambda can be anything still, right? So I'm not going to divide, but that's okay because I have just lambda x now equals lambda y. So now just bring everything over to one side. Lambda x minus lambda y equals 0. And if we do that, then we get GCF, pull out lambda, and you get two solutions here. Lambda is 0 or x is y, right? Set each of those equal to 0. Let's look at the lambda 0 first. Can lambda be 0? No? Why? Yeah, if this is 0, lambda 0, that's 0, and then those two multiplied together would have to be 0, which means one of them would have to be 0. But I already said none of them are 0, right? So this is not even possible, which means x has to be y. That's looking pretty damn good, right? Yeah. Now what we do is probably take the other two equations, like that, and do the same thing. Let's see if we can get some relationship there. We're just going to follow the same game, right? And hope that things go away and at the end we get something nice. So let's do it. I'm going to erase this part. I'm going to go ahead and distribute now. So we've got 2 lambda yz plus lambda xy. That's me going here, 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 here. That must equal this one, here, 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 here. So 2 lambda xz plus 2 lambda yz. Do we get similar cancellation like we did a minute ago? Those are gone, right? Those are gone. Subtract that on both sides. That will leave you with lambda xy equals 2 lambda xz. I can divide both sides by 2. I can divide both sides by x. I cannot divide both sides by lambda, although I know that when I let lambda be 0, nothing's going to work, right? I'll have to throw it out, but I can't do that yet. Oh, wait, I'm not dividing by 2. Sorry, not dividing by 2. They both don't have 2's. I'm going to divide the x's out, though. So we've got lambda y equals 2 lambda z. Bring everything over to one side. I'll do it right here. Lambda y minus 2 lambda z equals 0. Factor out a lambda plus y minus 2z equals 0. And that means that lambda must be 0 or y must be 2z. And lambda can't be 0 for the same exact argument that we had before. Pardon me?
So that we could divide.
Well, no, because nowhere in here am I saying lambda can't be 0 in the beginning, right?
Okay.
Right? So what I'm doing is I'm saying what happens if lambda is 0 now? Like if it's 0, then I have a problem up here. All right. I have two relationships, right? After all this work, in order for this to all work out, right? In order for this to all be satisfied, these at least, these three, I have that x must be, was it y?
Yep.
And then I have that y must be 2z, right? Those are the things I have. And I have not satisfied the fourth constraint yet. So what I'm going to do is I'm going to try and get everything in terms of a single variable, like either x or y or z. I think for me, what I see the easiest thing to do here would be replace x with y. Anywhere I see x over there, replace it with y. And then here, let me just take half of this on both sides. Half of y equals z. I can replace z with half of y. So everywhere I see x, it's going to be replaced with y. Everywhere I see z, replaced with half of y. And I'm going to go into the fourth equation now. Equation 4 becomes 2. Now x we just said was y times z, but what's z? It's half of y. Plus 2 times y is just y, z is half of y, plus x, which was y, times y, which is y, equals 12. You see how every x got replaced with y and every z got replaced with half of y? And now I can start cleaning this up. It's a single equation with one variable in it. So half of 2 is gone, half of 2 is gone. So this is just y squared plus y squared plus y squared equals 12. 3y squared equals 12. Y squared equals 4. Right? And then square root. So you're supposed to do plus or minus, but remember earlier we said y can't be negative. So we only have one answer here. Y is 2. Y is 2. If y is 2, what's x? X is 2. And if y is 2, what's z? Half of that, 1. There we go. Yeah. So that's it. Now, how do we know that that's a maximum? How do we know that that's a maximum, though? We never really supposed anything, right? And this is the only result we got. What did we threw out x being 0 or y being 0 or z being 0. Didn't we throw that out? So the reason we know that this is a maximum is because if you try anything else, like x being 0 or y being 0 or z being 0, if you try that, you're going to get 0 volume, aren't you? You're going to get 0 in the volume of this thing right here. So we know that compared to any other value of x, y, or z that we plug in, it'll be smaller than this, right? So this for sure is where we have a max. It's just an argument by, it's like the obvious only scenario this could be is this is a maximum. Couldn't possibly be a minimum. So we don't have the answer yet, right? It says find the max volume and then what are the dimensions. So remember our box was like this It was x, y, z. We know that x has to be 2, right? Y has to be 2. Z has to be 1. And then the volume of that, you multiply, right? X times y times z. The volume is 4 cubic meters, right? Would be your volume. And it happens when your x is 2 meters by 2 meters by 1 meter. That's the way you build the box.
So even if you switch up those dimensions, there's no reason for x to be x and z to be. Those are just variable holders. We can still move around. Like say
No, because it's an open top box, it has to be, the x and y have to be 2. Like you couldn't make that 2, then this 2, and this 1. Because the box is open on top. So that would impact it. If the box was completely enclosed, like top, bottom, then yeah, it would change that over there.
you would have to change your wording to say a size or something like that. Yeah, if you were to change that effectively, you would have to argue that also the size of the root size.
From your picture, from your answer from your picture, sorry. Stop. Okay. Your picture has, we had labeled x, y, z in our picture, so my answer was x is 2, y is 2, z is 1. That's where I'm being explicit about which side is which. Okay, look at example 8. We're not going to do example 8, we're just going to talk about it. Find the maximum volume of a rectangular box with a double bottom if it is made from 81 square feet of cardboard. That's the exact same problem, but instead of, let me draw the box. We have a box. This does not say that it has an open top, does it? So we assume that it has a closed top on it, but it's made of a double bottom, reinforced the bottom, right? So you have one layer of cardboard, another layer of cardboard. So if we label this x, y, z again, the volume is exactly the same, isn't it? X, Y, Z. The difference is the constraint, because the total surface area is different formula, right? We have what this one here is xz, another backside xz, so we have two xz's. Plus we have the two sides here, right, which are yz, two of those. Plus, we have the top, which is xy, and then the bottom, but it's doubled. So we actually have 3 xy's instead of, in the previous problem we did, wasn't that just 1 right here? And also equals to 81, not 12. So that would be your constraint, and then you just run through the same thing. So it's a slightly different problem because of the 3 here and the 81, of course. So your partials are going to be a little different. Yes? Do a what?
You ever have to suppose since x and y can't
You don't have to suppose. No, we never, see, when we did our drawer conclusions in the previous one, we never did suppose, right? We just said, let's start working with this. Now, we did state the condition of the problem was that all our variables were positive, right? Which is the way I would start this one as well. I would say, hey, look, it doesn't make any sense to make any of the sides 0. So let's start with that condition that all variables are positive. Then you're going to get one answer, which has to be your maximum. And then that's, whatever it is.
So you don't have to go through all the steps of testing.
Like, okay, so now let's let x be 0. You don't have to. No. All right, so I'm going to leave this as just, we're going to move on because it's such a similar problem, right? Find the point or points on the sphere x squared plus y squared plus z squared equals 4 closest and farthest from a certain point. Let me show you a visual of what's going on here. We have a sphere, right, sitting in 3D, and we have a point that I've given you. That's not on the sphere, it's just some other point. And what we're trying to find are 2 points. one point that is closest to that black point, which is the blue point, that lives on that sphere, and we're trying to find the red point, which is the furthest point away from that black point, but on the sphere still. So there's 2 points on that sphere, one that's closest and one that's furthest away. We need to find out what they are. That's the geometry of the problem. For us, what we need to do is somehow turn this into a Lagrange. So right away, I hope it's obvious to you that we have a constraint that we have to live on the sphere, right? Our answers must live on the sphere. So my constraint over here on the side, my equation, well, I'm not going to say if it's equation 3 or 4. I'm just going to put the constraint over here. I know that that's my constraint and that this right here is my g. And since my g is a function of 3 variables, I know that by doing Lagrange, this is going to be equation 4. What I need now is the f. What is the function that I'm trying to find the maximum and minimum of? And we're talking here about distance, aren't we? We're talking about a distance. Find the points on this sphere that are closest and furthest from this point. So when we talk about distance between 2 points, we have a formula for that, right? We talked about this in the very beginning of class. The distance between 2 points. So if I give you the point x1, y1, z1, right, and the point x2, y2, z2, the distance between those two is the difference of the x coordinates squared plus the difference of the y coordinates squared plus the difference of the z coordinates squared. That's from way, way back in the beginning of this class. And I probably didn't use x1, y1. I probably used like ABC or something like that. Yeah, so, but it's the same idea. It's difference of the x coordinates squared plus difference of the y coordinates squared plus the difference of z coordinates squared, square root. That's your distance formula. Now for us, this is arbitrary, right? This is like any 2 points. We actually know one of these points, right? One of those points is the point 3, 1, 3, 1, negative 1. The other point, on the other hand, we don't know. That's what we're trying to find out, right? So I'm going to call that point we're trying to find, I'm going to call x, y, z. So I'm going to, instead of calling this, I'm going to call this x, y, z, and then that's going to be 3, 1, negative 1, like that, and I'm going to rewrite the formula. So that my distance is square root of, see, x minus 3 squared plus y minus 1 squared plus z plus 1 squared. All right. Is this a function of 3 variables? Could this be our little f? Yeah, it could be, right? Now, we have to make a decision as a class right now. From calculus 1, right? When you're trying to minimize or maximize a distance, you can actually, instead of looking at the distance, you can look at the distance squared. So like whatever x, y, and z makes this the smallest would be the same x, y, and z that makes this without the square root the smallest. Whatever x, y, and z makes this the biggest would be the same x, y, z that makes that the biggest if you take the square root out. So in other words, to maximize this means to maximize the radicand. To minimize this means to minimize the radicand, that thing under the root. So would y'all like me to leave it with the square root or to adapt the problem to the property that I'm just trying to optimize the radicand? Radicand, everyone? Yes? Okay. So what I'm going to do instead of this is I'm going to say, I'm going to be looking at my f of x, y to actually be that distance function squared, which will eliminate the root, which will be the x minus 3 squared plus the y minus 1 squared plus the z plus 1 squared. So that is my f function that I'm trying to find when this is the biggest and smallest, and I'm subject to constraint that I must live on that sphere. And now we get to start cranking out the Lagrange. Let's remember though, whatever answers we get, right? If we get x, y, and z, that if we truly want the distance, we're going to have to go back to this, right? Whatever x, y, and z we get, we don't plug it into f if we want the true distance. We have to plug it into this to get the true distance. Or in other words, take the square root of whatever answer we get, right? Take the square root of it. Okay, partials. So my f of x, y, z is okay. First equation, partial of f with respect to x equals lambda partial g with respect to x. Second equation, partial f with respect to y equals lambda partial g with respect to y. Third equation, partial f with respect to z equals lambda partial g with respect to z. Okay, partial of f with respect to x is kind of interesting because these don't have x's. I just need to do a little chain rule on that. So it just becomes 2 times x minus 3. That's it. That's your chain rule. Bring the 2 out. That to the first power. Derivative of what's inside is just 1. So that's it. That's your derivative. Equals lambda. Partial g with respect to x is just 2x. Okay, on this second one, partial of f with respect to y is 2 times y minus 1. And then equals lambda. Partial g with respect to y is 2y. Partial of f with respect to z is 2 times z plus 1 equals lambda times 2z. Do we have a condition that x can't be 0, y can't be 0? We don't have that this time, do we? Or do we? Can it? Can x be 0? X could be 0, couldn't it? There is a way that x could be 0 and we could still land on this sphere. Y could be 0, we could still land on the sphere. Z could be 0, right? Now, can they all be 0? They can't all be 0. Okay, that's fine. Okay, great, whatever. I'm not going to set any suppose yet, all right? Because right now I don't have anything. I just want to just go with this. I think what I'll do here is,
Could you solve for lambda for 2 of them?
you could solve for lambda for all of them if you wanted to, but if you solve for lambda here, you have to divide by x, right? Which means you have to promise me x can't be 0. So we will have to go back and look at that if you want to, right? Actually, let me look at my notes. I did this 2 different ways, so let me see which way I did it.
Why don't you just divide up the 2 and then bring the x plus 3 to x minus 3 over through addition?
Wait, say again?
Wouldn't you just be able to divide out the 2? And then
Divide
bring
out the
x
2.
minus 3 over?
Yeah, you can.
Yes, that's one thing we could do is just get rid of the 2's here and just solve it like a little linear equation.
Yeah.
Yeah, we could do that.
Exactly.
We could do that here as well. Let's try and do this without, as much as possible without making any like suppose this. Let's try and restrict ourselves from that if we can. So kill the 2's here. Can we kill the 2's here? Kill the 2's here. That I can do. I don't have to make any suppose for that. And then y minus 1 equals y, lambda y. Z plus 1 equals lambda z. Okay, that's just it cleaned up. Now, here's what I'm going to do. I'm going to bring this x term to the left. I'm going to take the negative 3 to the right. That's just my choice. I can move everything to the right if I wanted to. I just wanted to make that a positive 3, so I moved it over. So I get x minus lambda x equals 3. And then GCF. That's all I can do here, GCF. Right? And then I could divide right now by 1 minus lambda to get x, but then I have to promise you that lambda is not 1, right? Okay. Remember, you cannot set each of these equal to 3, right? That's something I talked about in my algebra class this morning, right? This only works if that's 0. Then you can set them each equal to 0. But if this is not 0, you can't do that. So the most I can do here is this. Let's suppose that lambda is not 1, right? And if lambda is not 1, then I can divide both sides, and I can get x is 3 over 1 minus lambda, right? I can do that. so long as lambda is not 1. Let's look at this one. Bring everything over to the left. Bring the y's to the left. Take the negative 1 over there. Factor out again. And then divide through. I'm still supposing here that lambda's not 1. Okay, so lambda's not 1. I've got this. Lambda's not 1. I've got this. Yes?
Like you said, I thought you can't do that because you didn't set it to 0. That's assuming that the scalar value is not initially inside of
Wait, did what?
So what you did is essentially you made 1 minus 0 and you solved for.
I didn't solve for anything? I'm saying I cannot divide both sides of this by 1 minus, because to get from here to here, I divided both sides by 1 minus lambda, right?
I understand.
And I'm just making sure that you understand that I am aware that that 1 minus lambda can't be 0. And the only way to be sure of that is if I tell you that lambda is not 1.
Right.
Right.
Like you said that we can't do that. So well, let's say we do that same thing, but for x, we can't do that because it's inside of the set. I'm confused. So we can't say x equals to 0, x cannot equal to 0, and assume that because we have a 3 on the other side. Why can't we do that for the same thing for 1 minus lambda when we can do the same?
I'm not setting anything equal to 3. Look at what I'm doing, okay? I'm not setting this to 3 and setting that to 3. That's not what I'm doing. I'm taking this and I'm dividing both sides by something, and I'm doing it in a way that I'm promising you that what I'm dividing by is not 0. That's not the same as setting it equal to 3. Got it? Okay. All right, over here, same thing. Actually, yeah, I'll bring it over. This will be negative 1 this time. So bring everything to the left, take the 1 over to the right, divide through again, and you get an equation here for z. So as long as lambda is not 1, right, this is what x is, this is what y is, this is what z is. The reason I did that is because now I can write x in terms of lambda, y in terms of lambda, z in terms of lambda. I can go into this equation, replace x, y, and z with those things with lambdas. Then I'll have a single equation with nothing but lambdas. Then I'll solve for lambda. Once I know what lambda is, I come back here, I get x, y, and z. Right? That's where I'm headed. So there's another way through this problem, but we chose this way, right? We chose to not divide both sides by x here, okay? Maybe we look at that after this. I don't know. If we want to, we can. That's another part of grading these I don't like, is because there's more than one way to go about it. Someone might do something different, and so our work might look different. Okay, equation 4. So here we go. I'm rewriting equation 4. I'm replacing x with 3 over 1 minus lambda squared, plus replacing y with 1 over 1 minus lambda, square that, plus replacing z with negative 1 over 1 minus lambda squared. That must be 4. We square each one of those. So when you square this, you get 9. Square the top, square the bottom, 1 minus lambda. I'm not going to square it.